Hi Pre-Calc, welcome to our first video. We're following along in our text, if you want, on section 1.1, sets in the Cartesian coordinate plane. The first thing we're going to look at is, what is a set? A set is basically an organized group of numbers or letters that all have something in common, or they're well defined. We just are describing a group of things, and a lot of times it's going to be numbers, but we can also use letters. So my name is Laura, L-A-U-R-A, and so I'm going to use that as an example for defining our set in a few different ways. So we're going to define our set using the roster, verbal, and set builder methods, and then I'm going to talk a little bit about notation, which just means a way of writing things. So the first way I'm going to describe my name, set L, we'll call it, is using the verbal method. So I'll write down what we would say using the verbal method. So here's what we would say. L is the set of letters that are in the name or word Laura. Then we can describe this using the roster method. And roster, if you think about roster of a baseball team or something, it's literally just a list of all the members of the team, all the players. And so it's just listing something. So that's what we're going to do for the roster method. It's literally just listing. So this is the name of our set, set capital L. And then we're going to make these fun brackets. And then L, comma A, comma U, comma R. Now, I'm not going to write A again, even though that's how you spell my name, because I already included A, and you only have to include each element one time. These are called elements. They're just the pieces, or the letters in this case, in the set. They're all the objects in the set. So this set has 4 elements, and that is the roster method of just listing. Then we'll take a look at set builder method, and set builder method is sort of a combination of both the verbal and the roster methods, and it looks like the most mathy. Here's the set builder method. So we're going to say that L, again, is brackets. L is every single, and then we're going to use a dummy variable, in this case x, since x is not a part of our set. So L is all x's such that x is a letter in Laura. And we'll see that if it's a more mathematical set, such as using numbers instead of letters, we'll see that set builder will look a little different, but this is the main idea, is that we have brackets, we say all x such that x is whatever is in our set. And then let's talk a little bit about notation. Notation, just how we write things. Our set L has 4 elements, so we would say, and we know those elements are L, A, U, and R. So we could say that A is an element of set L. We know that the letter E is not in my name, so it's not in set L. So we would say that E is not an element of set L, which is just this little symbol with a line through it. Just like if you say not equal to, which is an equals symbol with a line through it. So that means is not an element of. So that's just one example of what a set is, and we'll see some more sets later on using numbers rather than letters, but I thought that was just a more fun example than numbers, which we'll see a lot more of. We classify numbers with sets of numbers. So we'll classify these two in just a second. I found these graphics online and I really like them. So they show the same thing. This is just more fun. Rainbow colors here. So the real numbers are what we'll use this year. We will also explore non-real numbers or imaginary and complex numbers later on, but for now this is what we really care about. The real numbers are a giant set of numbers. There's an infinite amount of elements in them, and they're composed of both the rational and the irrational. So the reals are this big set of numbers, infinite, and the rationals and the irrationals make up the reals. Now, rational numbers are ones that can be put into a fraction or ratio. Literally, the word ratio is in there. Ratios or fractions are any number that can be put into a fraction, or if it's a decimal, it's a terminating decimal, meaning it ends, or it is a repeating decimal. It has a pattern. Irrational numbers are ones that if you put these into your calculator, you would get a non-repeating decimal that goes on forever. That's irrational. Inside the rationals are three smaller subsets. So the integers are part of the rational numbers. The integers are like numbers on a number line. The whole numbers are just a part of that number line starting at 0 and all the positive integers. And the natural numbers are the numbers you first learn as like a kindergartner, starting with 1. They're all the positive integers. Sometimes these are also called the counting numbers. Here's another graphic that shows the real numbers. It's less exciting, but it shows the real numbers again being made into the irrational and the rational. The irrational numbers are decimals that go on forever, non-terminating, and they have no pattern. Here are some examples. And then the rationals, which is represented by Q, can be made into a ratio or a fraction. So numbers like 1/4, 3, 0, 0.9 repeating, or this terminating decimal 3.57. There are an infinite number of examples we can put there. And again, inside the rationals are these three other sets: the integers, whole, and natural, or counting numbers. So we just talked about a couple things, and I'm going to write those down. We said that the rational numbers, which are abbreviated using a Q, and I put this like extra little line here to show like boldface. I know that wasn't in the graphic, but that's how you can write it. Real nice. Okay, so the rational numbers is any number that can be written as A over B, or a ratio, right? But A and B both have to be an integer, so they are elements of the integers, which is shown with a Z. So both A and B have to be integers. And what do you think B cannot be? B cannot be 0. So a rational number is defined as any number that can be written as a ratio, A over B, where A and B are both integers, like 1/4, or -7/2, or 3/1, and B cannot be 0. Every rational number can be put into this form. If it can't be, then it's irrational. So rational numbers include terminating decimals, so decimals that end, and they also include repeating decimals. Irrational numbers, on the other hand, which are represented by I, irrational numbers cannot be put into the form A over B, and they include non-terminating, which is just a fancy way to say it goes on forever, non-terminating decimals with no pattern. So pi, for example, is probably the most common irrational number, the most famous. Pi goes on forever and does not repeat. Another example is the square root of 2, or E. Okay, let's classify just a couple numbers here. I just made up 2 examples. So the -17 is our first number. So can -17, it's a real number, can it be made into a ratio? Is it a rational number? Yes, it is, because it can be written as -17 over 1. And -17 and 1 are both integers, and 1 is not 0. So as we can clearly see, this technically is a decimal. It terminates. It's -17.0. That's another reason to say it's a rational number. So it is a rational number, but we also want to see how far it goes inside the rationals. It's real. It's rational. Does it go further? Is it an integer? Would it be on a number line? Yes, it would be. Does it go further? Is it whole? No. The whole numbers do not include negatives. So, -17 is a real number. It's rational. And it is an integer. Most specifically, it's an integer. When we say something's an integer, we know that it's also rational and real. Let's take a look at the square root of 10. If you don't know what the square root of 10 is, put it in your calculator, hit enter, and you'll see that it is a decimal that goes on forever and ever and does not have a pattern. 10 is not a perfect square. Therefore, this crazy decimal cannot be put into a ratio of two integers. We can't do that. And so the square root of 10 is an irrational number. Now it's real, so it is both real and irrational. Now, how do I know all these numbers are real? Well, if you remember back to Algebra 2, numbers that aren't real are those that include I, which is imaginary. We're not going to be dealing with those yet. They're not even on this graphic. So we just classified numbers using this nice graphic here. If you want to find one, Google the real number system under images, and you'll find plenty that look really nice. Okay, on this next slide, we're going to be writing sets of numbers in interval notation. We can see here that this first example says every single x is in this set, every single x that's greater than or equal to -2. Now, that doesn't just mean the numbers on the number line greater than -2. This is every number. Numbers like -2, -1.9438, 0, pi, 4.7, 18, 3 trillion. Those are all numbers that are greater than or equal to -2. So if we write that as an interval, the smallest value that we can be is -2. And we can go all the way to infinity since it's everything greater than it. Now, we can't ever capture infinity. We're going to put an open parentheses around it. We're also equal to -2. We can equal it, so we're going to put brackets around it. What does that look like on a number line? Well, if we wanted to graph this answer, we'll sketch a little number line, put the number we care about on it, and we can include -2, so we'll put a closed dot, and then it's everything greater than -2, so we'll graph to the right. In this next example, this is a set that includes every single number less than 5. Numbers like 4.9 repeating, 4, 0, -3.7, -4 trillion and 1. Every single number that's less than 5. To write that as an interval, we can go all the way to -infinity, and we cap at 5 since it's less than 5. Infinities always have open parentheses, and in this case we're not including 5. We're buttoned right up to 5, but we can't include it. There's nowhere equal to. So we're going to put the open parentheses around 5 as well, since we can't include it in our answer. On the number line, we'll put a 5, and then we're going to use an open dot or an open circle, since we're not including 5, but it's everything less than 5. Okay, these next two are not going to an infinity. In this case, this set has every single number that's between -1 and 4 and including 4. So we'll do that as our interval, -1 to 4. And then we can't include -1, but we can include 4. So that's the difference between the brackets and the open parentheses. On our number line, we have to include both numbers since they're both important. And we're going to have an open circle above -1, but a closed circle above 4. And it's everything in between. The last one's very similar. It's all values between 2 and 5, non-inclusive. So we're not including 2, nor are we including 5, so open parentheses around both. Our number line will look like this. And so this is a way that we can write values in interval notation. Now, this seems kind of like a random idea to include here, but interval notation is a super common way to write solutions to any problems that we'll see this year and that you'll see beyond this year, beyond pre-calculus. So interval notation is super important to know, and it's a lot easier, I think, than writing in this set notation or graphing. So interval notation is important to know. Remember that any infinities have open parentheses, and this closed bracket means you're including that answer, whereas the open parentheses means you're not including that answer. Okay, this next slide I'm going to go through quickly because we should be knowing how to do this stuff, but there are 4 quadrants on a Cartesian coordinate plane, and it's Cartesian. We're just not dealing with like polar coordinates or anything like that. This is just the basic coordinate plane that you know. It's called Cartesian. So there's 4 coordinates, and they form a C, if that helps you, just like that. So this is the first quadrant, the second quadrant, the third quadrant, the third quadrant, and the fourth quadrant. Points that lie on either the x or the y axis are not in a quadrant. All right, let's graph a couple points. Let's graph point A. A is at 4, -2, so we're going to go to the right 4 and down 2. And then point B is at 0, 3, so we're going to go 0 left or right and then up 3. This point B is not in any quadrant. It's actually on the y-axis. The x value is 0, anywhere on the y-axis. Point C, we're going to go left 1 and down 5. And then point D is at 4, 0, meaning we're going to go to the right 4, and we're not going to go up or down at all since the y-coordinate is 0. Point D is not in any quadrant. Instead, it's on the x-axis. Notice that the y value is 0 on the x-axis. For this problem, we're going to use points A and B to show how to find the distance between 2 points using the distance formula, and then finding the midpoint, the coordinates of the midpoint of a line segment, or the distance between 2 points. All right, I just wrote the distance formula down. I do not specify, like textbooks will specify x sub 1, x sub 2, y sub 1, y sub 2. You don't need to do that. You're just subtracting the x values and subtracting the y values. Now, the distance formula actually is derived from the Pythagorean theorem, which you can also use to find the distance between 2 points. The distance between 2 points would be the hypotenuse. But let's just use the distance formula. It's pretty straightforward. So D is distance, so the distance will be, we're going to first subtract our x values, and our x values are 4 and -4. Now, the order that you're subtracting these does not matter, and that's because you're going to square them anyway. So whether or not we do -4 minus 4 or 4 minus -4 and get -8 or 8, doesn't matter. We're squaring it anyway, which will get us the same answer. So I'm just going to do A minus B. So 4 minus -4, and then we'll square it. And then I'm going to do the same thing to the y values. I'm going to do 1 minus -3, and then square it. So 4 minus -4 is 8, so we'll get 8 squared plus 4 squared. Under the square root, that gives us 80, 64 plus 16. So we actually end up having root 80. Now, the square root of 80 is an irrational number. It's almost 9, because it's almost the square root of 81. And since 80 is not a perfect square, the square root of 80 gives us an irrational number. But that doesn't mean that this can be our final answer. We want to break down a square root if we can. So we want to think, what's the biggest perfect square that's going to fit into 80 perfectly? What is the largest perfect square factor of 80? 16 is the largest perfect square factor of 80. 16 times 5 gives us 80. And so we can break down the square root of 80 into the square root 16 times square root 5. The square root of 16 is 4, so we'll cross it out, bring it out, and we'll get 4 square root 5 as our final answer. And that is the distance between A and B. So what we can do is we can write that AB, which is the distance between A and B, is 4 root 5. All right, the midpoint formula is actually really easy. We're finding the middle, the coordinate smack dab in the middle between A and B. And so the midpoint formula is a coordinate point. It's half of the sum of the x's and then half of the sum of the y's. So it's x plus x over 2. and then it's y plus y over 2. We're averaging. We're finding what's right in the middle. Remember, to average something, you add up how many there are, or you add them up and divide by how many there are. Well, there's 2 x's and there's 2 y's. So the midpoint between a and b, in order to find that, we would do x plus x, or negative 4 plus 4, the 2 x's, divided by 2. And then we would do negative 3 plus 1. So this yields 0. 0 over 2 is 0. And the other fraction will yield negative 2 in the numerator, and then we divide that by 2 to get negative 1. Let's quickly plot it and see if it's in the middle.